Next up on our discussion on angular motion, we have moment of inertia. Consider now an object that is moving in a circle of radius r, moving at speed v. So you have an object moving in a circle, speed v, radius r. For now, let's say the speed v is constant such that it doesn't matter where in the circle you look. The speed of the object will be speed v. Now, as far as the circular motion is concerned, speed v is the tangential speed of the object as it undergoes circular motion, as it undergoes angular motion. Now, we know from our angular kinematics, we know that there is a relationship between the tangential speed and the angular velocity of the object. Angular velocity omega is equal to plus minus v over r, where v is the tangential speed of the object and r is the radius of the circular motion. Now, the plus minus sign refers to the direction of the angular motion. Positive if the object is moving in the counterclockwise direction, and negative if the object is undergoing clockwise direction. Getting the magnitude of the angular velocity for the most part, that is the angular speed. Again, for the most part, not always, but for the most part, magnitude of the angular velocity is angular speed is equal to v over r. We remove the plus minus sign because that refers to the direction of the angular motion, and we are just talking about the magnitude of the angular velocity. Transferring r to the other side, we have equation for the tangential speed. V is equal to omega r. The object is moving, therefore, it has kinetic energy. Kinetic energy is equal to 1/2 mv squared. Now, v here, the speed of the object, is the tangential speed. So, we can replace v by omega r, and we get 1/2 m omega squared r squared. We can group together m and r squared. So we have 1/2 quantity of mr squared times omega squared. Comparing this equation with the original equation of kinetic energy, 1/2 mv squared. So you have 1/2, 1/2. You have m, you have quantity of mr squared, and you have v squared, you have omega squared. So 1/2, 1/2, v speed squared, angular speed squared, so basically speed squared. So m, this is a counterpart of m. mr squared quantity is a counterpart of m. Since we have omega here, angular speed, this, which is rather omega is the angular counterpart of v. That means mr squared is the angular or rotational counterpart of m. So that means 1/2 mr squared omega squared is the rotational counterpart of the kinetic energy 1/2 mv squared. Let mr squared be equal to a quantity I. I is equal to mr squared. Kinetic energy now becomes rotational kinetic energy. This equation is now the rotational kinetic energy 1/2 I omega squared. And I is equal to mr squared. We refer to I as the moment of inertia of the object. Unit is kilogram meter squared. So, 1 kilogram meter squared. I, moment of inertia. I, again, is the rotational counterpart of m. And just like mass, the moment of inertia of the object is conserved. So I total is equal to just the summation of the individual moment of inertia making up the system or making up the object. So again, I is equal to mr squared. Now as mentioned, moment of inertia may be thought of as the rotational counterpart of mass, rotational inertia. In kinematics, angular kinematics, you will recall theta is the rotational or angular counterpart of x. Omega is the angular counterpart of v. Alpha is the angular counterpart of a. For linear motion, we use x, v, and a. For angular motion, we use theta, omega, and alpha. The same goes for mass and moment of inertia, I. For linear motion, use m. For angular motion, use I. Now, note that the above equation, this equation of the moment of inertia, I is equal to mr, as it turns out, is only applicable for this situation. You have an object moving in a circle of radius r. As it turns out, I depends on the location of the axis of rotation. For an object moving in a circle of radius r, the axis of rotation, the center of the rotational motion or angular motion or circular motion, the axis of rotation is far away from the object, separated by distance r. If the axis of rotation is near or touching the object, you have different equations for moment of inertia. For example, say you have a solid cylinder or disc. So you have a solid cylinder, radius r, and length L. Say the axis of rotation is passing through the center of the cylinder or disc, and the disc or cylinder is rotating around that axis of rotation. The moment of inertia is given by 1/2 mr squared. On the other hand, if you have a hoop or a ring of radius r, if the axis of rotation is passing through the center of the ring or hoop, the moment of inertia is mr squared. So moment of inertia for a hoop or ring is mr squared. On the other hand, if the axis of rotation rather is passing along or lying along the diameter of the ring or hoop, the moment of inertia is different. So same ring but different orientation of the axis of rotation, you have a different moment of inertia. 1/2 mr squared. And then if you have a sphere, a solid sphere of radius r, and the axis of rotation is passing through the center of the sphere, the moment of inertia is 2/5 mr squared. And if you have a solid cylinder or disc of length L and radius r, and the axis of rotation is passing through the middle of the cylinder or disc, as shown, the moment of inertia is given by 1/4 mr squared plus 1/12 ml squared. If the radius r is very small, compared to the length L, you have a slender rod. The moment of inertia is now 1 over 12 ml squared. So R is very much smaller than L. So this term is negligible compared to the second term. I is equal to 1 over 12 ml squared. And if the axis of rotation, instead of being in the middle of the rod, is at the end or edge of the rod, the moment of inertia becomes 1/3 ml squared. And if you have a hollow sphere of radius r, so previously we had a solid sphere of radius r, the moment of inertia was 2/5 mr squared. Now if this solid sphere is instead hollow, you have a hollow sphere, the moment of inertia is 2/3 ml squared. These equations of the moment of inertia are just a few examples of the different equations for the moment of inertia. Consider it as a reading assignment to look for the other equations of moment of inertia. For instance, there's also the moment of inertia of a rectangular plate. What if instead of a solid cylinder, you have a hollow cylinder, and so on? So consider that as a reading assignment. Look for other equations of the moment of inertia. We can also use what is called the parallel axis theorem to determine the equation of moment of inertia. We can use the parallel axis theorem if we know the moment of inertia at the center of mass of the object. Moment of inertia, ICOM, moment of inertia for axis of rotation passing through the center of mass of the object. And the actual axis of rotation of the object is parallel to the center of mass axis. So, two requirements for us to use the parallel axis theorem. We need to know ICOM, the moment of inertia for axis of rotation passing through the center of mass of the object, and the actual axis of rotation of the object must be parallel to the center of mass axis. Must be parallel to this axis. Okay, center of mass axis. That's why parallel axis theorem. So you have an object, say a disk, center of the disk, we have the center of mass of the disk. If the axis of rotation is passing through the center of the disk, we know the moment of inertia of the disk. 1/2 mr squared. If the actual axis of rotation of the disk is not at the center of mass, but located here, parallel to the center of mass axis, the actual axis of rotation of the object is a distance h from the center of mass axis, parallel. We can use the parallel axis theorem. And the parallel axis theorem tells us that the actual moment of inertia of the object is equal to ICOM plus mh squared. Again, ICOM is the moment of inertia with the axis of rotation passing through the center of mass of the object. And the two axes must be parallel. The center of mass axis and the actual axis of rotation of the object. I is equal to ICOM plus mh squared. The center of mass, consider that some of you might want to explore the concept of center of mass. Put simply, the center of mass is the point at which the mass of an object is considered to be concentrated, at least as far as the motion of the object is concerned. The object moves as if its mass is concentrated at the center of mass. For regular shaped objects of uniform mass distribution, the center of mass is located at the geometric center of the object. A cylinder is basically a regular shape. The center of mass is at the geometric center of the object, assuming uniform mass distribution. So all the shapes that we have shown earlier, solid cylinder, ring or hoop, sphere, rod, these are all regular shaped objects. The center of mass is located at the geometric center of the object. Again, you have different equations for the moment of inertia. For an object moving in a circle of radius r, I is equal to mr squared. And this equation is applicable only for this situation. Object moving in a circle of radius r. And then for other equations, you have different shapes. You have different equations for the moment of inertia for the different locations of the axis of rotation. And that's it for now. In the next video, we'll continue our discussion on angular motion. In the next video, we'll take a look at the concept of torque, which is basically the rotational or angular counterpart of force. So once again, that's it for now. Thank you for watching.